So students, very good morning to all of you. And today I'll be talking about eigenvalues and eigenfunctions. And so let me write down eigenvalues and eigenfunctions. All right. Now, corresponding to any dynamical variable that we have in classical physics, in quantum mechanics, we have a corresponding operator. Suppose we have position as a dynamical variable. In quantum mechanics, for position, we have position operator. Then we have momentum. Momentum is a physical quantity in classical mechanics. And how do we measure it? We say momentum is the product of mass and the velocity of the object. That gives us the measure of the momentum. And for this dynamical variable, we have an operator in quantum mechanics. Similarly, energy, right? So energy is a dynamical variable. And for energy, we have an operator in the quantum mechanics. So we call it energy operator. And in the similar way, angular momentum. So angular momentum, being the dynamical variable, has a corresponding operator in quantum mechanics. Hamiltonian, which gives us the measure of the total energy of an ideal system, which is basically the sum of kinetic energy and potential energy. For Hamiltonian, we have an operator in quantum mechanics. So if I take my operator as, say, x cap, I would take a generalized operator, right? So x cap is an operator. Okay? Now, if I define this operator, say for example, I define this operator as d by dx, right? This operator I choose as d by dx. And I define a wave function, say, I define a function in general, say psi of x. And I define this psi of x as a, say I will define it as sine of theta. So what we have an operator and we have a function, say psi of x. Now, if I operate this operator on this function, what will I get? I will have x cap of psi, right? X cap of psi of x. So what will be that equal to? That will be, for x cap, what's the operator? It's d by dx. So I will have d by, I should choose it x here. D by dx of sine x. So your operator is acting on this function, and what you obtain cos of x. So what is your observation? Your observation is you have an operator x. This operator is defined as d by dx, and you act this operator on a function, and that function is defined as sine of x. But when you operate this operator on this function, you get another function. You get another function, is it? So if I have to generalize this thing, what am I doing? I'm using an operator on psi of x I am getting phi of x. Clear? Right? Now let me choose another example. Now if I use my psi of x equal to sine of x, and I choose my operator as the double derivative with respect to x. Right? In the first case, what we had an operator, we operated it on a function, and we got another function. Now, what I'm doing is I'm using a different operator, right? And this different operator is defined as the double derivative with respect to x. And I'm acting this operator on my function. Now, if I do that, how would I write it? It says x cap psi of x is d2 by dx2 sine of x. Right? Right? So, you will take the double derivative of sine of x, you will get cos, then you'll get minus sine. So what you get x cap as sine of x is minus sine of x. So what do you observe from this result? You observe that the operator that we defined, we acted this operator on a function psi of x. By making this operation, we obtain the same function. We obtain the same function. So, this was beautiful, man, because there's no chalk on my hand, right? So, this is x cap psi of x equals minus 1 times psi of x. Now what is this minus 1? It's a real number. It's a real number. And this real number is called eigenvalue. This is called eigenvalue. And the wave function that you have, this wave function is called eigenfunction. So I can say this is an eigenvalue equation. In the left-hand side of this equation, we have the operator acting on a wave function. You may also call this wave function as a state vector. And when you do that, you obtain a number and the same wave function. There are two things. The first thing is that it's an eigenvalue equation. The second thing is that this operator that has given you the same function after making an operation, this operator is called Hermitian operator. What is it called? It's called Hermitian operator. Is this clear to you? Fine? Can I move on? Okay. So what we have an operator acting on psi, and I get a number. Let me call that number as lambda psi of x. I think in the previous lecture we actually solved the problem, eigenvalue problem, when we were talking about the infinite scarable problem, right? You had a particle in a one-dimensional box, and you calculated two important things for that particle. One was the energy, and the other thing was the eigenfunction. You remember that? Okay. So what was that? It was something like this. We had H, the Hamiltonian operator. It was acting on psi of x, and you obtained the energy eigenvalues En psi of x. And when we solve, this is Schrodinger's equation, right? H is the Hamiltonian operator and En are the energy eigenvalues. So when we have solved this equation, what we obtained energy eigenvalues. You remember what were those energy eigenvalues? It was En equals n squared pi squared h squared by 8ml squared. These were your energy eigenvalues. So the point is that corresponding to an operator, you can have a range of energy eigenvalues because n can be 1, 2, 3 and so on and so forth. This is how it goes. And if you rightly remember, we obtained the energy eigenfunction. You remember that? And what was that energy eigenfunction? That energy eigenfunction was psi n. And what was that? That was under root of 2 by L sine of n pi by L times x. Right? So this is an example. So what we were basically doing in that lecture was we were solving an energy eigenvalue equation. We were solving the Schrodinger's equation, and by solving the Schrodinger's equation, we obtained the energy eigenvalues for the particle in that one-dimensional box and the energy eigenvectors. So what was our basic thing was we had an operator and we operate it on psi and we obtain a number and the same function. Now, for the operator to be Hermitian operator, there is a necessary condition for that. There is a mathematically necessary condition for an operator to be a Hermitian operator, right? And what is that? That is, suppose I have an operator, this operator is acting, and you have the energy eigenvalue, and you have the same wave function. Now, for this operator to be a Hermitian operator, what is important is integral minus infinity to infinity psi star x psi d tau, if I take it over the whole volume, must be equal to integral minus infinity to infinity x cap star psi star and psi d tau. If this condition is valid for an operator, then we can say that this operator is a Hermitian operator. And what is important here is that the wave function psi, it has to be a well-established normalized wave function. This condition, this criteria can be obtained only if the wave function under consideration is well behaved, well established normalized wave function. Clear? Now, what does that normalization mean? That means the integral minus infinity to infinity psi star psi d tau must be equal to 1. Now, another question arises here, minus infinity to plus infinity. Now, what should happen to the wave function? What should happen to this wave function at minus infinity? And what should happen to this wave function at plus infinity? The value of this wave function should vanish at minus infinity and it should vanish at plus infinity. Is this clear? Right? So, if I write down this thing in terms of x taking only one dimension, because we always feel comfortable writing down things in one dimension. So I can write down this as minus infinity to infinity psi star of x, then I have an operator x, psi of x is equal to integral minus infinity to infinity x star psi star of x and psi of x dx. All right. So for the operator to be the Hermitian operator, what is important is that this condition should be satisfied. But what I did here, I assumed that corresponding to one operator, I have one energy eigenvalue and one energy eigenfunction. What if I have two energy eigenvalues with two energy eigenfunctions? I have a problem. I obtain two energy eigenvalues and two energy eigenfunctions. How would I define the condition for the operator to be a Hermitian operator? Right? Is this clear to you? So when this condition is met, you will say that this operator is a Hermitian operator. Okay. So now what am I assuming is I assume that I have psi1 as one energy eigenfunction and psi2 as another energy eigenfunction. Right? Now, how would I write down the condition for the operator to be a Hermitian operator? Okay, how would I do that? I would write integral minus infinity to infinity psi, so I define the operator x cap. Right? So psi 2 star of x and then x cap psi 1 of x is equal to integral minus infinity to infinity x cap star psi 2 of star of x psi 1 of x dx. Now what is important here is that you have two energy eigenfunctions, and these two energy eigenfunctions, if you have to satisfy the condition, if you have to obtain the condition for them to be Hermitian, what you will do is you will have to satisfy this condition, right? But this condition can be satisfied only. What is to be presumed in this equation is that integral minus infinity to infinity. What I said that these wave functions. Now we are dealing with two wave functions. Now these wave functions must be well established wave functions. They must be well balanced and they must be completely normalized wave functions. So the wave functions should be normalized. So what does that mean? That means from minus infinity to infinity, psi 1 star, psi 1 dx must be equal to 1. And integral minus infinity to infinity, psi 2 star, psi 2 dx must be equal to 1. You can obtain this condition only if you presume that the wave function psi 1 is normalized and the wave function psi 2 is normalized and the wave function psi 1 vanishes at plus minus infinity and the wave function psi 2 vanishes at plus minus infinity. Is this clear? Is this clear to you? Yes. So the next thing that we have to discuss is, now what I said I have an energy eigenvalue equation. What is that? You have an operator this operator is acting on the wave function, and what we obtain, if we obtain lambda, if we obtain the real value, and we obtain the same wave function, so this is my energy eigenvalue equation. And what are the important components of this equation? It has an operator x. This operator is acting on the wave function psi of x. And when you operate this operator on the wave function, if you come up with a real value, then your eigenvalues are real. And at the same time, you come up with the same wave function. You come up with the same wave function. Now, the next thing is that how can we say, I think it is a point of mathematical predictability now, that what we want is, we want to prove mathematically. We want to prove mathematically that this lambda has to be real. It has to be real. Clear? So for that, we will have to do an exercise. We'll have to do an exercise on this problem. So how can we do that? What's my argument? My argument is, you have a Hermitian operator. If your operator is Hermitian, it acts on a wave function. What you get is a real number. This lambda is a real number. And your original wave function is back when you are operating this wave function psi of x. Right? How will I do that? I will choose psi 1 of x. I will choose two energy eigenvalue equations, and then I will try to prove that this lambda has to be what? This lambda has to be real. Do you have any idea how can I do it? So I will choose my psi 1, okay, and I will be using an operator on this psi 1, and I will be getting lambda psi 1, right? Any problem with it? No. And I'm using this x cap star. You remember the condition? The equation, the left hand side, integral psi star x cap psi dx has to be equal to integral x cap psi star and psi, right? So that's the condition that I'm trying to use here. So this is my first energy eigenvalue equation, and if I take the star of this operator, star, you understand? The complex conjugate. Star means complex. If I take its star, psi 1, I will get lambda star. I should call this lambda star psi 1. Okay? Right? Now, let's go to the condition. What's the condition? What is the condition? The condition is minus infinity to infinity psi star of x cap psi dx is equal to integral minus infinity to infinity x cap star. Look at it. What is it? X cap star and then psi star psi dx. Clear? Okay. So psi star, x cap and psi. What is x cap and psi equal to? It's lambda psi of x. Remember? So this is, it's here. You can check it. So this is lambda psi. Okay? So I have used 1 here. You can use it as general as psi. So what will I write here is psi star, yeah, lambda psi dx. Is it clear? Is equal to integral minus infinity to infinity. Now, the operator, the star of the operator operating on psi star gives us what? It gives us lambda star psi d of x. I think I have committed a mistake here. Okay, here it has to be the star. Okay, you'll correct it. This was wrong. Okay, so you have to keep star here. So you should take this out. Don't go with 1. You go with psi. You can do it with psi. All right? Come on. Okay. So I can move this equation on the left-hand side, right? What is my aim? My aim is to prove mathematically that when you have a Hermitian operator, this operator acts on a wave function, you will always lead to have real energy eigenvalues. That's my job, right? So, what I do now, yeah, come on. This is integral minus infinity to infinity. Then you have here psi star, then you have lambda, then you have psi, then you have dx, then minus infinity to infinity. Then you have again psi star, then you have lambda. Okay, this is lambda because lambda star, sorry. Lambda star and then psi and then dx is equal to what? Is equal to 0, isn't it? Okay, what is common in this equation? I think integral minus infinity to infinity psi star psi dx is common. And what is inside? Lambda minus lambda star is equal to 0. You remember the presumption? You remember the presumption? The presumption was that the wave function has to be normalized. It's a normalized wave function. You have a product between this integral and this thing. Their product is what? Their product is 0. If their product is 0, either of the two things has to be 0. Right? But what is real for us? Real for us is that this integral is what? This is equal to 1. So this integral is not equal to 0. Then what is equal to 0? Lambda minus lambda star is equal to 0. So integral minus infinity to infinity psi star psi dx, this is not equal to 0 because it's a normalized wave function. Then what is equal to 0? Lambda minus lambda star is equal to 0. That means lambda is equal to lambda star. Lambda is equal to lambda star. But what's my presumption? What am I supposed to prove? I'm supposed to prove that the number that you will get is a real number, right? Now, if this lambda is, see, this minus this is what? 0. This minus this is, isn't it? This minus this is 0. Suppose lambda is, say, a plus iota b. What will be lambda star? A minus iota b. Right? Their subtraction has to be equal to. Their subtraction has to be equal to. So if their subtraction has to be equal to 0, what does that mean? That means you will get only real number. Isn't it? So this lambda minus lambda star, or I can say this lambda is equal to lambda star. It can be only equal to lambda star when the complex part will vanish. When the complex part of the lambda and the lambda star will vanish. Only then the two lambdas can be equal. Only then the difference between these two lambdas will be equal to 0. So this is how we prove that when we act a Hermitian operator on a wave function, we always come up with the real energy eigenvalue. So if you have any questions, you can ask me. Right? Okay.